start them. Okay, so welcome to the session on complexity classes, NDTMs and reductions. So what will we actually cover? Today we'll cover the complexity classes, what they are, P, NP, NP complete, EXP, and NP hard. We'll cover NDTMs and how they actually define NP, reductions and how they define NP hard and NP complete. So before we start on the actual complexity classes, let's do a quick recap of big O notation. I know you guys have done this to death probably, and are probably done with this, but big O notation is a way of defining a worst case scenario for the program. So you can think of them as like smaller time bound complexity classes. So when we're working with big O, we assume all of our programs take an input size of n, and big O returns us a rough amount of steps the programs will take. So if we have like f of n that iterates over its input, the program will have O of n. But g of n will have O of 1 if it takes the first element in an array, because that doesn't change depending on the input size. And that's all I really wanted to cover for big O. So complexity classes. What is a complexity class? A complexity class is defined as a set of computational problems where the problems in the same set have similar resource complexity. So what I mean by resource complexity is that the problems in the same set are bounded by space and time. So they take similar amount of space and time to run. But just note, I said similar, but similar doesn't necessarily mean close. So a program that runs in O of n to the 7,000 might be considered similar to a program that runs in O of n squared. So more on this just like literally right now. So our first complexity class is the complexity class P. P is a complexity class of problems and programs that run in O of n to the k. And they're considered fast in comparison to other problems. So these problems are matched in polytime, which means, like I said, it runs in O of n to the k. And to be matched or recognized means that the machine M will correctly determine whether the language, whether the given input X holds a given property. So in a more maths notation heavy way, L is in P if and only if there exists a machine M that takes an input of n and is in O of n to the k such that M of X maps to true if X is in L, and M of X maps to false if X isn't in L. So you can see that the machine M kind of like recognizes what is and isn't in the language. I'm sorry if I sound a bit ill. It's because I am. So a few problems that run in polytime are like sorting, searching, basic arithmetic operations. All of these things run in polytime. So before we move on to NDTMs, is there any questions about that? Oh, sorry. Okay. Yeah, the session's being recorded. Okay, so does k have to be in the natural or can it be real? I'm pretty sure it's natural numbers. And if k is less than 1, is it still considered polytime? No, because if k is 0, then that's constant time. Does that answer all the questions? Oh, Discord is very laggy. Yeah. Thank you, Witty. This code's really doing my head in. Is it really that obvious? Okay, so NDTMs. So before we understand the NP complexity class, it's first vital that we understand what NDTMs are. So an NDTM stands for non-deterministic Turing machine and is a Turing machine that has one extra function from the normal ones, which is the choose function. So when the machine reaches this function, it may go down the path of 0 or 1, which happens entirely at random. So that gives it its almost like non-deterministic aspect about it, because the machine isn't ensured to go down the same path every time. And because of that, the values that are accepted by a non-deterministic Turing machine are called acceptable and unacceptable, as opposed to accepted and unaccepted. But much like a normal Turing machine, the words that are acceptable to a non-deterministic Turing machine make up its language. So despite the choose function, non-deterministic Turing machines can still recognize languages. Which leads us to the NP complexity class. So to be considered in the complexity class NP, a language or problem must be recognized by a non-deterministic Turing machine where each individual run of the machine, occurs in polytime. So, i.e., if the language L is the language of the non-deterministic Turing machine and each run occurs in polytime, L is in NP. And so, yeah, previously I described P as being fast. And remember, this is relative to very slow problems. Problems in NP are harder and tend to be difficult to solve, but easy to verify the solutions of. So like if you can imagine, like if you gave a random like regular person a scrambled Rubik's Cube, it would take them a while to solve. But once it is solved, you can easily tell that it is solved. Which is kind of like NP, because the solutions are difficult to generate, but once they've been generated, we can tell in polytime if they actually solve the problem. Right, so, oh my God, I'm sorry. All right, so it's great that we have a new complexity class that can be defined by a non-deterministic Turing machine, but in our exams, it's not always intuitive to think of NP as only one non-deterministic Turing machine, as it can be quite abstract and like difficult to actually implement. So this is where the other definition of NP comes in. So we can actually think of NP as two things: a deterministic Turing machine and a possible solution, which we call like a candidate. So imagine we have the language L and we want to verify that it's in NP. So imagine now we have a generating machine we'll call G. The machine G generates a candidate word that may or may not be in L, along with its certificate X, where X is, we say it's like polynomially bounded by W, which means that relative to the size of W, X is a polynomial. So if W is like a size of N, X can be like N or like N squared. And X is called a certificate because it certifies that W is in L if a path to an accepting state exists in the non-deterministic Turing machine. So next we have a deterministic checking machine M that accepts an ordered pair input, so the word and its certificate, and then verifies that the word is actually in the language L. So I like to think of a certificate as like a map that helps navigate the checking machine towards the accepting state in the non-deterministic Turing machine, if that makes sense. Does that make sense so far to everyone? Wow, Discord is very laggy. South Park Dr. Mephisto. Okay, right, okay, cool. So just to conclude, since a valid certificate will only be generated when W is actually in the language, the ordered pair WX will only be accepted when W is actually in the language. So if W in L is synonymous, like the same as the machine accepting the ordered pair, so the machine only accepts that, then and the process occurs in polytime, then we can say surely that L is in NP. So this definition differs from P as generating a solution for NP doesn't have to occur in polytime. It can be like exponential. So a few examples of problems in NP is like the satisfiability problem. So specifically the formula sat, which is given a propositional formula, decide whether or not it's satisfiable. So guessing an assignment of the atoms in a propositional formula is linear, but generating specifically a satisfiable assignment, if one exists, can be O of k to the n in the worst case, but checking the solution is always going to be linear. And another one is the factor existence problem. So given a number n and k is less than n, say whether n has factors less than or equal to k. So that's in NP, as we can generate two numbers that are less than k and then check it. Right. Before we move on, does anybody have any questions? Is the stream still going? Can everybody hear me? My Wi-Fi tends to be a bit bad at home. Okay. Okay, cool. So I'd just like to do like a couple of exam style questions because I feel like NP is what we're going to be asked the most questions on. Because like NP complete and NP hard was literally like one sentence in the handout. So I feel like this is really, the meat and potatoes of it. So consider the following problem. Given a set of integers, say whether it has a subset that adds up to 0. So for example, if we're given this set, we can return this set because this set adds up to 0. Of course, it's not the only solution, but we only need to find one. So if we're given this set, we can return impossible because there is no subset that adds up to 0. And we have to show that this problem is in NP. Just a little hint, you don't need to fully draw out a Turing machine. We just need to do these three things. Define what a candidate solution would be, say why the size of the candidate would be polynomial, and then explain why it takes polynomially many steps to check the solution. So would you guys like to work through it alone, or do you want me to walk through the answer? I assume that's just walk through the answer with you guys. Okay. Oh, okay. You can, but it's easier to actually not draw the Turing machine. Shay, is that you wanting to speak on stage? Yeah, come onto the stage. Hello.
Yo.
Hi.
So, if you have a candidate solution, it would always be a subset of the input, right? So it would always
Right.
be less than or equal to n. So
Mhm.
then when you're checking it, you're checking no more than n values. So it's polynomial relative to the input.
Right. Okay. Yeah. That's pretty much it. So are you going to explain why it would take polynomially? And yeah, well, I mean, you did. Yeah.
Um,
Sorry.
yeah,
But
yeah, you can just check every number, like
yeah,
one by one linear.
right. That's pretty much
And then
it.
it's done.
Yeah. Good
Yeah,
job.
just
Does everybody understand what he meant by that? Does everybody get it? Oh, I'm lucky. Okay, cool. So that's basically what I've said here. A candidate solution would be a subset of the set we're given, and it would be polynomial because by definition, a subset has to be equal or less than the size of the set. And it would take polynomially many steps because at most you just check the size of the set. All right, here's another question. Just so you know, it warned you on the exercise sheet that this was harder. So for a given alphabet sigma, let L and L prime be languages in NP. show that the intersection between these two languages is also in NP. So yeah, you want to use the checking definition of NP for this one. And so yeah, like the previous one, you only need to describe the machine in outline with these three things. So define what a candidate solution would be, say why the size of the input would be polynomial relative to the input, the size of the candidate would be, and then explain why it takes polynomially many steps to check the solution. So would you guys like to work through this one too? Okay, does anybody have a solution to this? The checking machine definition of NP tells us there exists a machine that can check the ordered pair W and the polynomial. Okay. Oh, invited to speak. Okay, cool. Hello.
Hello.
Hello. Yeah, I can hear you.
Yeah. So we could define a candidate solution first, right? That's the first
Yeah,
step.
that's the first step.
So candidate solution would be a set of words which
Yeah,
would have, like, let's say A and B in it, where A and B and all the words would be inside L, and all the words would be in the set L apostrophe. What do you call that? L prime, L
L prime.
dash,
Yeah, L
L
prime.
prime. Okay, L prime. So it's inside both of those sets.
Yeah,
And then second step was say why the size of the candidate would be polynomial relative to the input.
yeah,
So in this case, the size of the input is the two languages, right?
right,
So let's say if that's n, the size of the solution that we're checking is going to be either equal to n if both of them are the same language, or
right.
are less than that, because it's an intersection, right? So
Yeah,
we'll only take stuff that's either, like, it has to be in both of them. So that can't be more than any of the, like, it can't be more than the smallest language out of those two, basically.
okay, yeah.
So therefore it's smaller than the size of the input, therefore it would be in, like, polytime.
Right. Sorry, I think
And
I actually put it on the slides wrong. That's meant to say certificate, not candidate. But yeah, that's a big mistake. Sorry. But yeah, do you have a reason why the certificate would be like? What would the certificate be also? Do you have like any solution for that? Sorry.
what, like the candidate solution?
The what would be like a certificate for the problem?
What, like one that we can verify that works, kind of.
Yeah, like yeah. To be fair, the answer that they had was pretty
Like what? Just an
abstract.
example. Like L has 1, 2, 3. L prime would be 2, 3, 4, and it would be 2, 3. Like that
Could
would
it
be
be the sum?
then 2, 3 could be verified in polytime.
Um, 2, 3. Yeah, I mean, like the solution that they had doesn't actually use like examples. It's actually like very abstract. It doesn't even like reference any like example at all, which is a bit weird. What do you say, Shay? Sorry. Could it be the sum? What do you mean by the sum? Oh, the certificates of the numbers is the sum of those numbers. Because we can get the solution later on. So the checking machine takes, for example, returns true or false. Um, to be fair, like the sum of the numbers. The languages don't necessarily use numbers. No. This new question, we're explaining why the intersection of two problems in NP are is also in NP. For all W and are you talking about reductions? It's nothing to do with reductions. Okay, go through this one. Do you guys you say what like a certificate okay, right. I guess we'll just go through it. Okay, so the solution for this is, so suppose the certificate for a word in the intersection of these two languages would be a certificate for L and then a certificate for L prime. And the machine, the checking machine, would first start by checking the first half of the certificate certifies for L and the second half certifies for L prime. And so the explanation for this is, since the certificate overall is just two certificates appended, and we know that the certificate will be polynomial since, okay, bear with me, each individual certificate already certifies for an NP problem. And by definition, to certify for an NP problem, that certificate would have to be polynomial. And a polynomial plus another polynomial would just be another polynomial. And since we know that those individual problems are both in NP, checking one and then checking another one after is still going to be in polytime, because checking each one of them individually happens in polytime. And we don't have to change anything with the word because the word is just in both of them. We don't need like two words or anything, even though it's two languages. Does that make sense to anybody? I assume there should be questions. My Wi-Fi might actually be a bit shit right now. I'm so sorry. Can everybody hear me? Did everybody get that? Okay, great. Good. Get it? Okay. Yeah. So the certificate is just a certificate for L, and then concatenated, like appended on the end, is a certificate for L prime. And the machine checks the first half is a certificate for L, and the second half is a certificate for L prime. Okay, I guess we'll move on if nobody has any questions. So I honestly just put this in here for the meme, but we've talked about a couple example problems. So I guess we'll talk about the problem, P versus NP. Is a certificate just an example solution to the problem? No. Well, okay, so a candidate is an example solution to the problem, and a certificate is what the machine uses to like verify that work. Okay, right. Okay, so if we have, for example, take this, right? This question here. Yeah, I guess you'd be right. Like a certificate would be an example solution. Because we used this to certify that this word is in our language. The condition for a candidate solution has to satisfy to be verified. So, okay, so we have a problem, and we want to verify that this word is like a valid thing in this problem. Like this actually has a subset that adds up to 0. This would be a candidate solution, a certificate for this word, because this subset adds up to 0. Does that make sense? So is the language of valid problems? What do you mean by that? The solution is a candidate, but the certificate is the conditions we need for a solution to satisfy the problem. Yeah, I think you're onto it, Ashbit. Yeah, that's it. Yeah. Like, so that so it's in this language. I don't know what you mean by defines, but like, so imagine there's a language that can tell whether or not a set has subsets that add up to 0. This is our like property, right? And then, so we have words, like imagine this is just a word, right? The set is just a word. And we can also have like this set that's another word. This word is acceptable to that property because it has a subset, a valid subset that adds up to 0. But this word would be unaccepted because it doesn't have a subset that adds up to 0. So a certificate is just proof. It's like this set is a subset of this set, and this set also it also adds up to 0. So it's like proof that this like word is acceptable to that property. Yeah. Okay, cool. Okay, so the problem, like I said, I kind of put this in as like a meme, but the P versus NP problem, I'm sure you heard like Paul mention it at one point during the lecture, is one of the hardest unsolved problems in maths and computer science, and asks if P is a subset of NP or if it equals NP. So most people in the field tend to think that P is a subset of NP, but some problems in NP can be like reduced to problems in P. It's not yet known if it's possible for all the problems or only some. And the open question basically asks, can problems that are tough to solve, NP problems, be reduced into easy to solve problems? Because in the past, there were problems thought to be in NP, but after developing like new algorithms and stuff, we were able to actually see that this problem, when applied with this algorithm, is actually in P. But okay, so the reason I'm not going to give the solution of this one, heard you graduate with a first if you do. See guys, the reason I'm not going to be giving a solution is because of this paragraph right here. Do we really want P to equal NP? If P equals NP, problems such as prime factorization become very easy to solve because prime factorization is an NP problem. If that reduces into P, computers that rely on prime factorization to keep computers secure will fail. I obviously know the solution, you guys. I'm just not telling because it would be very bad. Moving on to the complexity class EXP. Oh. My bad, you guys. I accidentally crossed out of exit out of Discord. Okay, hope. Okay, it's still recording somehow. Real FBI is captured. Bro's being targeted by the FBI. I just have too much knowledge. Okay, sorry. The complexity class EXP. So this complexity class contains slower and harder to solve problems. Am I screen sharing? Okay, I'm screen sharing. Okay. All right. So these problems are matched or recognized in O of k to the n, and there are no weird definitions or strange machines we need to understand. EXP problems are just matched by a regular Turing machine in O of k to the n, where k is some number in the natural numbers. What is this? What is this big moment, Witty? Why are you so... Okay, so... Okay, people are typing. Can you still not see my screen? Okay, okay, cool. Oh. Right, okay, I guess nobody has questions. Right, so in the same maths notation way I define P, L is in EXP if there exists a machine that takes an input of n and is in O of k to the n, such that m of x maps to true if x is in L, and m of x maps to false if x isn't in L. And that's literally all you need to know for EXP. So before we tackle the rest of the complexity classes, we have to understand reductions, which Shay kind of described earlier with the LaTeX he put in. So a reduction is a way of changing a problem into another problem. This is going to get a little bit abstract, so I expect questions. Don't be afraid to put questions in the chat. And despite what reduction may suggest, it doesn't explicitly mean that one is necessarily easier or harder than the other, but simply that one problem can be seen as another. Although we will reduce easier problems to harder problems and vice versa, and use it to sometimes refer to how difficult problems can be in very specific cases. So I'll often use A as what's being reduced and B to describe what it's being reduced to. So reductions only imply that if we have A and B, and we know that A reduces to B, if we have a solution for B, then we have one for A. So, which is quite useful later on. So assume we have two languages, L and L prime. A reduction is a function f that takes words in L and sort of translates them into words in L prime. So again, in maths notation, L reduces to L prime if there exists a function that maps words to words such that when x is in L, f of x is in L prime. Right, before I move on, does everybody get that? Yep, okay, cool. So there's a few rules to this though. If a problem B is in P and A reduces to B in polytime, we can say surely that A is also in P, because if you have a solution to B in polytime, you have a solution to A in polytime. So when a problem of an unknown complexity class reduces to a problem in a known complexity class in polytime, it sort of like inherits that complexity class. Sorry. So if you were in the logic module, I think it's pretty obvious that if you have a reduction from A to B, that doesn't necessarily imply a reduction from B to A. Okay, so if And if every problem in a known complexity class reduces to one of an unknown complexity class in Polytime, we can surely say that the unknown problem is of equal or harder difficulty. So if A is in P and B is in some mystery language, in some mystery complexity class rather, and A reduces to B in Polytime, we can say that in terms of difficulty, B is of equal or harder difficulty than A. That's going to be later. Don't worry, Ollie. Does that make sense? I'm sorry that I'm dying, by the way. Sorry. So would that mean that L is a subset of L prime? L is in P. So, yes. Yeah. Yeah, so L would be a subset of L prime. Or at least the set that L prime is in would be a superset of L, or the complexity class that L is in, if that makes sense. Yeah, okay, cool. So this brings us to the NP hard problems. So NP hard is a complexity class, and as the name implies, contains very hard problems, like the halting problem, that are known to be like completely unsolvable. And so this class is defined entirely by reductions. So assume we have a problem X, and all of the problems in NP can be reduced to X in Polytime. So remember that a problem inherits the complexity class it's reduced to. So in this case, since all of the problems in NP reduce to this mystery, problem, this problem X with a mystery complexity class, we can say that here, this problem X must be of equal or harder difficulty than NP. And so X must be in NP hard. And because of the way reductions work, yeah, that means that this problem X must be of equal or harder difficulty. So in a more maths definition way, X is in NP hard if for all Y in NP, there exists a function F that maps words to words, such that for each word in Y, F of that word, so F of W is in X, where F reduces in Polytime. That's a very important thing. The main important parts of this that make it different from like a regular reduction is the fact that it's all of the words in the complexity class and the fact that it reduces in Polytime. Does that make sense before I move on? Okay, I'll take that as a yes. Okay, so the NP complete class is a class of problems that are both NP hard and in NP. So assume we have a new problem P that is NP complete. P is NP hard, so because it's NP hard, it must be equally as hard as NP or harder than all of the problems in NP. But P is also in NP, which means it cannot be harder. So it has to be like the hardest of the problems in NP, which is a bit abstract to say, but does that make sense to everyone? Yeah? Okay. Cool. This might help you visualize it a little better. So the NP hard problem, since all of the problems in NP reduce to problems in NP hard, in Polytime, NP hard has to be harder or like just as hard as the hardest problems in NP. And NP complete is where these two overlap. An NP complete has the property that once you've solved one of them, they all reduce to each other very easily in Polytime. So if you can solve one NP complete problem, you can solve all of them very quickly. And that's it. If you have any questions after this, please feel free to at me. Do you have any questions now? Is there anything that I missed? Anything you want me to elaborate on? Yeah, bro, promoting. W lecture, thank you. Professional, yeah. Sneaky plug. Yeah, okay, thank you. Thank you for listening. I will end the recording.